Right, that should work. Ah, there it is. I'll talk about this in a little bit, okay? Because that's obviously going to be somehow vaguely related to the subject of the talk, which is full stack developer. What do we mean by this? And I've been very, very careful with my punctuation. I'm not actually talking about what most people think of as full stack developer. If you've read the abstract, you will know this. If you haven't, you're in for a surprise. What I want to talk about is genuinely knowledge and techniques that can be illustrated. And it's just one day I worked out that actually messing about with just stacks, the kind of computer science's favorite abstraction, it turns out you can illustrate quite a lot. So just in time for this talk, a friend of mine, Chris Aldwood, put this wonderful quote up. The trouble with full stack developers is you can't push them. If you're not sure why that's funny, it's okay. I can explain afterwards, and also it will be available on video so that this is, you can find out why this is funny and then use it on your friends. So what are we going to talk about? I'm going to talk about romance to start off with. Love and romance. This is a picture of Stonehenge, and you might be thinking, what has Stonehenge got to do with love and romance? Well, I took this picture on Valentine's Day this year because my wife and I are obviously very romantic. We got up on Valentine's Day. The kids are off school. It's school holidays. It's like, right, what are we going to do? We're going to go and visit Stonehenge. That is how romantic we are. Okay, so forget bottles of wine and candlelit dinners. You go with your partner, and you show them rocks, arranged 4,000 years ago. There you go. That's real romance. So yeah, I was very pleased with this picture. Why am I showing you this? Actually, there's a reason I show you this, because mostly when people talk about full stack development, they're sitting there going like, oh, do we care about monolithic architectures? Monolithos, the Greek for one stone. Big, heavy stone. One big thing. We have a monolithic architecture. And in common with monoliths, these are surprisingly hard to move. Okay, that was one of the things my older son sort of said. He said, I've seen pictures of this, but I didn't realize how big they were. They're big, they're hard. It's like a description of somebody looking at a legacy system for the first time. Okay, how did they do this? Why did they do this? We don't understand what's going on. And it's so difficult to change. But then people sort of say, no, we have a solution. We've got a new architectural paradigm. Yeah, that's right, microservices. Yeah, so this is how we're going to build systems. Okay, we're going to go forward and we're going to build systems like this. It's like, you know what? Maybe there's other questions, because in both of these, there is a kind of a focus. We're very much focusing on the back end stack, and everybody's sitting there going like, here's the technologies that we want to use. So I want to draw your attention briefly. We're going to go through. We've done romance. Now let's do some popular culture. Michael Jackson. Now, you may have heard of Michael Jackson. There's a chance you may have heard of Michael Jackson. The requirements engineering guy. Yeah, you knew who I was talking about, didn't you? And he's done an awful lot of stuff and had a very strong influence on software development over many decades. In the 1970s, he was responsible for JSP, Jackson Structured Programming. 1980s, JSD, Jackson System Design. Both of these were really very influential and some really deep ideas in there. JSD in particular relates in some ways to an abstraction known as CSP, Communicating Sequential Processes, which I will cover later. Anyway, the thing about this, I mean, you look at this book and you're thinking, it's not the most exciting book title you've ever read. Software Requirements and Specifications. It's just like, oh, come on, really? But the subtitle tells you there's something else going on here. A lexicon, so it's organized alphabetically, of practice, principles, and prejudices. It's about 70 or so little essays between half a page and 4 pages long, just organized alphabetically, where he talks about software development with a particular focus on requirements. And he makes a very important observation. He says, too often we push the problem into the background because we are in a hurry to proceed to a solution. If you read most software development texts thoughtfully, you will see that almost everything is about the solution, almost nothing is about the problem. So we see this. It doesn't matter if we're talking books. It doesn't matter if we're talking blogs. We see there is a very strong focus for very solution-centric, which is okay, but every now and then we need to figure out what exactly is the problem. Now, we might think, oh, I have a solution to this. I'm going to go and buy Kevlin's book. No, I have a solution to this. I'm going to ask the customer. Now, in 97 Things Every Programmer Should Know, there's a lovely piece by Nate Jackson. Your customers do not mean what they say. And he highlights this, it's very true. He said, I've never met a customer yet that wasn't all too happy to tell me what they wanted, usually in great detail. The problem is that customers don't always tell you the whole truth. In fact, I think he was being, I was the editor and perhaps I should have changed this, but I think he was being relatively modest. The customers don't always, no, they never tell you the whole truth. Because it's actually almost humanly impossible to. They generally don't lie. It's not a question of honesty, but it's more a question of understanding where somebody else is coming from. They use their terms in their context. That's, of course they would. Why would they do anything else? Yeah, you're the person that knows about software. Why should they use your terminology? They leave out significant details because they just know. It's very difficult for somebody to simply describe something that they know and are familiar with in an educational style. That's surprisingly hard, to be able to educate somebody rather than merely just tell them what you're thinking. And even that's hard. And they make assumptions, of course they do. This is compounded by the fact that many customers don't actually know what they want in the first place. And again, this is nothing special that you get when you call yourself a customer. This is actually something you get for free when you're a human being. This is a kind of part of the human experience. You generally don't know what you want. And if you say that you know what you want, you will be surprised. So we go about and we say, right, what we got? System requirements. That's how we're going to do it. We're going to gather requirements. We're going to go out there as if the requirements were just sitting there in fields, waiting to be sown like corn. Basically, we're just going to reap all of those requirements. They're just lying there, waiting to be harvested. So people just write stuff out. Now, it turns out that writing is a surprisingly hard thing to do, okay? To try and put your thoughts down in a linear fashion, in a way that communicates everything that you are thinking and is significant and communicates to another human being. This is a non-trivial task. And then somebody comes along and says, look, nobody's going to read this. You need to kind of, break it down a bit. It's like, yeah, that's cool. I've discovered the bullet point functionality. Yeah, this is how we do our specifications. Oh, come on. Okay, so we need to have a point of view. And perhaps we need a little more structure than just a shopping list. Okay, good. Right, enter use case. So we've got a trigger. This is the situation under which the use case occurs. We've got a precondition. This is what must be true when we actually start this. In other words, this is for the use case to be successful, here is what must be true beforehand. Then we have a sequence of things that happens. And then we have a postcondition. This is what must be true after a successful outcome. Now, the problem is that this is not a universally adopted use case form. There are many different use case forms. That's actually kind of a bit of the challenge. People are not entirely sure what is a use case. And indeed, one of the bigger challenges, there's a couple of things I think that are worth tweaking. Rather than saying, here is the initiating action, let us go, first of all, let us describe the situation. When I'm thinking about things, I would rather describe, here's the situation, here's the thing that happened in it. Right, let's switch those around. And then we might also try and rearrange it. Rather than doing it linearly in time, we will use newspaper ordering, or it's also formally known as the inverted pyramid. Newspaper ordering is, if you're going to write documentation, give people the headlines first, and then give them the next most important thing, and then the next most important thing. This is not how we write stories, as in stories for children, stories for adults, films, or anything like that. We generally don't do this in this style, but this is how newspaper articles are written, because it allows you to just read the beginning, and you get a big picture view of everything, but you don't have all the detail. So here, precondition, trigger, postcondition. That tells you this is what must be true beforehand for us to be successful. Trigger, this is the inciting incident, the thing that happens that makes this use case interesting. And then postcondition, this is what is true afterwards. And then, if people really want, then they can read the sequence. Now, I know a lot of people who are locked up in organizations for what felt like years. I mean, historically, people used to go to jail and spend their time there, and then apparently in Britain we sent them to Australia. And then in the 20th century, we gave them use case sequences to write. I think that's possibly the cruelest thing to do. But there's a great piece of advice from the author, Elmer Leonard, trying to leave out the part that readers tend to skip. So we can just get rid of all of that sequence bit. It turns out it's the most boring bit to write and the most boring bit to read. And it has the added bonus of normally being wrong. So what we're going to do is we're just going to save ourselves a lot of time. So this is the first thing we notice. This is a skill. If I want you to think in terms of understanding the bigger picture, what are the skills that you need, then really just leave out the part that readers tend to skip. Just prioritize. Now, there's another interesting thing here. Wow, that's magic. So a lot of people say, oh, we don't do use cases, and we don't use preconditions and triggers and postconditions. Oh, no, we're using Bdd Stories. Oh, yes. It's a reinvention. The user story was inspired originally by use cases. Kent Beck is very explicit about this. But also, given when then, is it's a reimagining of precondition, trigger, postcondition. There's a very nice kind of 3-act play here that we find very useful. Now, so we think we now understand how to talk about requirements. Yeah, okay, let's just see how that works out. So, first of all, we need to, if we're going to talk about full stack development, we need to extend the stack. Normally, my experience is when people say, I'm a full stack developer, what I've discovered is that means they know some JavaScript and some Angular or some Node, and they know something about some back-end technology, and they know a couple of things about a database. Now, I used to be a systems programmer. It's just like, that stack goes a long way down, really a very long way down. If you ask a full stack developer, hey, so device driver writing, you ever written a device driver? No. Well, that's not much of a stack then, is it? Okay. So have you written the open source software that you are using? No. Okay, the full stack goes a long way down. It also goes a long way up. It touches out into the world. A full stack developer that doesn't really have a battery or an armory of techniques to go and talk to the customer or really understand the customer's situation is, again, only a partial stack developer. So let's just take this simple technique and apply it to, that's right, a stack, okay? It's a stack of books. This is a stack of books on psychotherapy, psychoanalysis. It turns out that psychotherapists are obsessed with objects, as you can see from the title. In fact, it would not be too far from the truth to just say that psychotherapists are obsessed, but that's a different story. Yeah, my mother was a psychotherapist. It's never done me any harm. Yeah, don't do this to your children, okay? Okay, so it's all about object relations, the shadow, it's all there. Okay, so let's talk about this stuff. We've got a stack of books, right? So we've got a stack. How do we understand a stack? It's got some things you can do with it. You can create it, push, pop, and you can find its depth, and you can ask its top element. This sounds like a good start, but let us try and take our way into this using the given, when, then form. It turns out this is a very useful conversational form at times, but people do still struggle with it, and we will see that it's not always the right thing. So first of all, given an empty stack, it's a good start. When an item is pushed, okay, then it should not be empty. Okay, so I'm not entirely happy about this because there's a couple of things here. I mean, one of them is the should word. I mean, some people find it very comfortable when they're doing BDD to use should. That's fine, but if we look properly at what words mean, should is a reflection of, you know what, maybe it isn't empty, maybe it is empty, who knows, who cares? You know, should is a very conditional word, you know? Yeah, so, I don't know, this talk should finish just before 6 o'clock, but hey, you know what, maybe it doesn't, yeah? If you're nice, it'll finish early. If you're not nice, I'll finish later, okay? This is how it works. So should is a very kind of like, well, I'm really not sure, and it almost doesn't matter which way it is. It's kind of like a very hesitating, it feels like when somebody says should, they're not really, telling you something. Then if it's okay with you, I think that perhaps it should probably not be empty, don't you think? It's just like, it's like talking to a teenager or a millennial. Okay, it's just like there's so much indecision, you're really not sure what it is that they're saying, but they're not very sure about it. So I'm going to go back. There's some really great old advice from Strunk and White on English writing. I love the self-referential nature of this advice. Omit needless words. Not only is it short, but it tells you what to do. Okay, it's just don't bother with this stuff. And it turns out that Strunk and White also had a very strong opinion about tests. And so they said, make definite assertions. They didn't talk a lot about mock objects, but they definitely talked about assertions. Make definite assertions. Avoid tame, colorless, hesitating, non-committal language. When a sentence is made stronger, it usually becomes shorter. Thus, brevity is a byproduct of vigor. Don't put in those noise words. People have already got enough words to get through. Okay, so with that in mind, let's go back to this. It is not empty. That's it. That's the end of the story. Okay, how many different kinds of empty are there? Turns out there's quite a lot. Okay, there's not, or rather, there's one kind of emptiness, but there's lots of non-emptiness. There's non-empty like the room in this cinema. There's non-empty like the universe. There's non-empty like the beer that I'm going to have later, and then that will disappointingly become empty. But there's a cycle there. We can explore that one. There's a point here, is not empty is not very specific. We should be specific. It has a depth of 1. Okay? If you want to think about this in terms of 32-bit signed integers, then there are 2 billion values that are wrong. Well, actually, strictly speaking, 4 billion values, but I'm going for the not empty one. So 2 billion values that are not correct. Having a depth of 2 would be wrong. Having a depth of 3 would also be wrong. Having a depth of 4, you see where I'm going. The point is, we can be specific. It's not about sometimes using programmatic language. I sometimes find that people, when software developers end up writing requirement-like things, they end up using all kinds of programmatic language. They end up saying sort of things like, well, the number of items is incremented by 1. And it's just like, no, people do not say that. That is not a thing that people do. See, look, I've got 2 fingers here. I'm now going to increment the number of fingers that I put up. No, I just held up a 3rd finger. That was it. There was no incrementing going on at all. That is not how humans speak. You can actually be surprisingly precise without being programmatic. Oh, and it's not just that it has a depth of 1. It has a depth of 1, and the top item is the item that was pushed. It turns out that doing this logic type thing is quite hard. You really have to forget. People often forget that. It has a depth of 1. Does it just have 1 of anything? No, it's 1 of the thing you put in there. And then we turn that into a method name. Yeah, that helped. Yeah, okay, so we're going to need a slightly better way of reasoning about this one. But logic is kind of going to help us, okay? It turns out that logic is quite a useful tool. Let's start off with a very simple observation from Jason Gorman. He kind of heads up Software Craftsmanship Conference in the UK. And he makes a very important observation. Given when then, there's a kind of universality to it, this 3-act play. It's not just precondition, trigger, postcondition. It's what we call a Hoare triple, named for Tony Hoare. It is basically the observation that given a statement or sequence of statements, an action, there is some precondition that if it is true when we execute S, precondition P, if it is true when we execute S, we will get the outcome Q. And it's upon this that all formal methods is based. This is logic. It turns out to be surprisingly useful when you're programming. But it also allows us to reason about and discuss our code more clearly. Okay, so let us try a more formal approach to dealing with our stack. Let's talk about ADTs, abstract data types. One of the key people in the abstract data type universe was Barbara Liskov in the 1970s. Well, she's still alive. She was the recipient of the Turing Award in 2009, I think, for her work very much on programming, language design, and paradigms, and distributed systems. And she made this point: an abstract data type defines a class of abstract objects which is completely characterized by the operations available on those objects. This might start sounding a little bit familiar. A programmer is concerned only with the behavior which that object exhibits, but not with any of the details about how that behavior is achieved by means of an implementation. So a really strict separation. And in fact, we can render this in very formal terms. And the only reason I'm putting this slide up here is it allows me to use an upside down A and a back to front E. What we've got here is really, we're trying to say for all types T, there is a stack that is this product. It has a new that gives us a stack, a push that takes a stack and a type T thing. So a stack plus a thing push, that gives us a new stack. In fact, we're going to come back to this later. There's an interesting implication of this. Pop takes a stack and gives you back a stack. Depth takes a stack and results in an integer. And top takes a stack of t and gives you a t. In other words, we've got the signatures here. Okay, well, this notation seems a little distant from what we're used to, so perhaps we revert it to something a little more like this and start sort of saying, well, you've got push of t and pop. Pop here, and indeed for the rest of the talk, pop is a pure pop. In other words, when you pop, you don't get a value back. We're going to do that for a number of reasons, one of which is simplicity, but one of which is it carefully works into something I'm going to show you later. So it's a really simple stack. And it's got a very simple set of signatures. Okay, so that's great, and maybe it satisfies some mathematical thing within you to have done it like this, and some programmatic thing within you to have done that. Problem is, I can get an interface out of that in Java very easily, but that's not really a stack, is it? I've got some names, but I haven't really given you much in the way of behavior. When we talk about interfaces, and this is quite important because we've ended up with a situation where pretty much from the early 90s onwards, and particularly from the mid-90s after the introduction of Java, the word interface has, when used on its own, has come to very much mean the language construct. And it's a set of signatures, and it's kind of blinded us to the fact that there is something deeper. It's not merely a set of signatures. An interface is a contract to deliver a certain amount of service. This comes from a paper published in 1983 by Butler Lampson, Hints for Computer System Design, which I do strongly recommend reading because it's still surprisingly fresh. There's a lot of really good ideas in there. And this was written a very long time ago. A lot of other things from the 1980s have dated, music, for example. Although for some reason my kids seem to quite like 80s music when I'm driving in the car. Maybe that's because I stopped talking about stuff like, hey kids, did you know what an abstract data type was? No, Dad, play the 80s music, okay? Clients of the interface depend on the contract, which is usually documented in the interface specification. I think that second bit's quite sweet. It's usually documented. You can tell he worked in a research environment. It's just like, yeah. Out here in the industrial wasteland of programming, where people get paid to do stuff for customers, documentation is not a thing that generally happens. So usually it's unusually documented. Yeah? We normally find that things are normally documented if they are open source. Yeah? They're more likely to be documented if they're open source than closed source. Okay, so we've got an idea. Contract. Now, the funny thing is that the word contract was used a few years later by Bertram Meyer. And this is a very interesting book, Object-Oriented Software Construction, published at the end of the 1980s. In fact, you can tell from the book cover, it's got a certain 1980s quality to it. He kind of popularized the term, and we still tend to use these days this term designed by contract to mean what he was talking about. But I think the contract is much, much deeper and richer than what he described, which is, in essence, just preconditions and postconditions. I think we can go a lot deeper than that. But also, we can also find a number of limitations. It turns out that the view that he was projecting in this book is actually does not cover all the situations as comfortably and easily as we would have hoped it would do. So let's go back to our friend the stack, and let's start annotating it without implementation, because it's an abstract data type. Let's focus on what is it that we want from each and every method. Okay, so we're going to focus on push first of all. Given that before, so that's is the depth, so I'm going to have a variable that is the depth before we call push. The post condition is the depth is whatever it was before plus 1, and the top is equal to the item that we push on. Okay, that seems reasonable. And then we're going to go for same kind of story. Pop, it's got a precondition. Before must be greater than 0. It must be greater than 0, so therefore no popping an empty thing. Post condition, the depth is whatever it was before minus 1. Now, actually, if we pause for a moment, there's something here that doesn't feel quite right. There's something missing. And it becomes a little more obvious when we go to depth. Depth. Given that the result is the depth, The postcondition is that the result is greater than or equal to 0. Well, that's a bit vague. You know, what can you tell me about depth? Yeah, it returns you a non-negative number. Yeah, but which non-negative number? I don't know. There's a few to choose from. Which one do you like? As a specification, this is really, it's not wrong, but it's really weak, you know. So, Kevlin, what's the weather like outside? Yeah, it's not snowing. Yeah, I mean, yeah, okay, so true, but not useful. It lacks specificity. We can do better than this. So actually, that's a bit vague. If we go back, pop doesn't tell you what the top item now is. Push doesn't tell you anything about the rest of the contents. And when we ask for top, we get this. This is the worst one of all. Top, precondition. I don't know. It can't be empty. What about the postcondition? I have no idea. What am I going to get? Who knows? Are you feeling lucky? It's like, In fact, the only one that's really precise is if we actually create a new stack. The postcondition is the depth is 0. And you can't call top, and you can't, oh, that's great. But notice, and this is a limitation, so I'm always a little bit bemused when people say, oh, yes, great techniques like design by contract. No, it's a great technique because somebody told you it was a great technique. They've never actually put it into practice, okay? When you put it into practice, you discover really quickly that it has limitations. The thinking model is very powerful, but in practice, it's filled with problems because it doesn't actually get you talking properly about the nature of the thing. You end up with silent bits of the conversation. So as a formalism, it has limitations, and people need to recognize these a little more clearly. Okay, so what can we do about this? Let's take a different formalism. Hey, same series of books. I did say I was going to talk about CSP, Communicating Sequential Processes. This is a formalism by Tony Hoare for reasoning about concurrent systems. And it turns out there's a kind of a simple logic to this. How do humans feel about multi-threaded systems? Well, they find them difficult, okay? How do they feel about single-threaded systems? Oh, they find them quite easy. Okay, tell you what, here's the clever bit. What we're going to do is we're going to pretend that everything is sequential, yeah? And then everybody talks to everybody else, but we never actually see any threads. It's a really clever sort of deceit. It's a sort of a nice trick because it allows you to reason through these things. However, I don't care about the concurrency bit just yet. We'll come back to the concurrency in a moment. What I care is there are some ideas here which I'm going to sort of pull out and reinterpret slightly. There is an idea called an alphabet. In one sense, it might be better called a vocabulary, but an alphabet. These are the things that we can talk about. What is it that we can talk about with a stack? Well, we can have a conversation about push, pop, depth, and top. In other words, this is the set of possible operations or actions or events. So that's its alphabet. Okay, well, we kind of knew that. Well, that's cool. And then we have a trace. The trace is interesting because what the trace is a list of all the possible meaningful interactions you could ever have with a stack. Okay, so we start off, so it's a set. We start off with angle brackets. That means it's an empty sequence. In other words, we create a stack and we do nothing with it. In the second line, we create a stack and we push something on it, and then we never see it again. We never do anything with it again. Third item, we create a stack, we call depth, and then never do anything with it again. Third one, we push something onto it, pop something onto it, then never do anything with it again. In fact, you can keep on going. As you might have guessed, this bit's quite long. It's sort of infinitely long. So, you know, if you have a junior programmer who's just joined your team, you can get them to write this out, okay? It'll keep them busy for ages. Or if you have one of those members of the team where whenever they actually develop code, it seems to have a negative effect, tell them, we've got a really important task for you. Formal specification. We need detail. Yeah, my previous talk was about detail. Yep, this is what it's about. We need all of this. So what we've done here is what we're doing is rather than talking about preconditions and postconditions, we are talking about effectively saying, what are the legitimate sequences? So one of the sequences you cannot call is create and then pop. Create, then top. Those sequences do not exist in the legal set of traces. This sounds all quite exhausting. It turns out that we do have a simpler way of doing this. It's called a state machine. Disappointingly, this will generate you all of that work that you got. What we've done is we've described the life cycle here. Again, there's this problem in software development that we get attached to one formalism. And we say, that's the formalism, and I'm going to use it everywhere. Okay? And you may have heard of the single hammer syndrome. I have this hammer. It's shiny, it's new, and then What happens next? Everything looks like a thumb. So there is this idea that we need to do. We need to explore. It's a case of like, okay, yeah, I like the pre and post condition model. I like the design by contract model. I like the given when then model. I like a lot of these things. But what you're doing is you're saying, oh, hang on, my set of skills tells me that instead of sitting here for an infinite amount of time writing out the possible traces, perhaps I could generate a grammar, so to speak. What I've got here is a description that is very easy to visualize, and people have sort of turned away from visualizations, which I think is a shame, because while some of them are terrible, some of them are great. We create a new object, it's empty. We push onto that, it becomes non-empty, okay? If you're in an empty state, you can't call top and pop because those aren't available to you, but you can call depth. In the non-empty state, you can call depth, top, push, and pop. And if pop is greater, if the depth is greater than 1, then we remain non-empty. If the depth is equal to 1, then we become empty. This is a really simple life cycle model. This is great. It turns out that there's a very simple way of capturing what we're seeing there. And it's not the other approaches. It's called unit tests. It turns out that actually, if we think about it from a unit test point of view, this is far more constructive. Let me just reformat this and then just drop out all of the noise. We've got a stack spec. We've got a new stack. It's empty. An empty stack throws when queried for its top item. An empty stack throws when popped. That's what we're doing with the unspecified behavior. An empty stack acquires depth by retaining a pushed item as its top. A non-empty stack becomes deeper by retaining a pushed item as its top. And a non-empty stack on popping reveals tops in reverse order of pushing. Now notice, this has a number of significant advantages over many of the other approaches, although I can cross-check it against my whiteboard state model, but unlike the design by contract model, the pre and post condition model, I've got the concept of history. I've got example data. I use example data. It turns out that humans are very much driven by example. We understand examples. If you just present abstract propositions, then your eyes eventually kind of glide off. You need to tell somebody, look, I've got a stack. I'm going to push this, and then I'm going to push another thing, and then guess what I've got in the stack? Well, let's just pop it and see what I've got, and let me assert on what I've got. So there's a really important point here. It's very, very concrete. And these are all propositions. They are logical statements. We've named these as logical statements and structured it using all the techniques we now have. Nesting. We avoid duplication in names by factoring that duplication out. Okay, so that's all. Okay, so I think we might have an understanding of a lot of the specification, but what about the implementation? Let's try that. So we've got a stack of T. I'm going to do this in terms of an array list. I've got depth, I've got top, I've got pop, I've got push. I'm going to throw illegal state exception for things that are illegal states. This seems entirely reasonable. Now, let's try something different. Let's try something very different that relates actually to the original abstract data type observation that I made about stacks. This is a mutable stack. Let's try something slightly different. Let's try using a persistent data structure. Now, persistent data structure, as Wikipedia tells us, is a data structure that always preserves the previous version of itself when it is modified. Such data structures are effectively immutable. The idea here is we are creating an illusion that nothing ever changes. We're able to share representation, and so therefore the old version persists. In fact, we can actually sometimes, I remember presenting this to somebody, I sort of said, yeah, the operations do not visibly update the structure in place, but instead always yield a new updated structure, and the view is all chained together. If you use version control, this is what you're getting. Okay? Don't confuse it with persistence as in databases. Okay, so what's that going to look like? Well, let's try and understand. Imagine that you have the simplest aggregate data type, an array, and we're going to treat that as a stack. A points to the front, that's great. B refers to that. The thing we're going to try and make sure of is that we're going to deal with immutable stuff, okay? So therefore, it doesn't matter if you share the same one. So therefore, B and A are both referring to the same stack, and there's nothing that I can do. Well, let's just try popping. C is the pop of A. Now, here's an interesting one, because now C is looking, what we've actually done is we have not modified A. The person looking at A is seeing exactly the same thing. We've not created a clone of the stack. What we've done, we've basically said, look, the pop of A is, well, move along one. Because you can't change the body, then it's effectively the same as having a separate stack. But this is the nice illusion. You can't really tell the difference unless you check reference equality. It's a little harder when we're going to do a push, so we're going to have to change the representation to something linked. That's fine. There's A. There's B of A. There's the pop of A. Now, the push is the clever bit, is that now it goes the other way. And you can actually have this forking out in memory. This is great. Now, this is actually a very old idea. It's like 1950s old. This is the basis of Lisp. Okay, the list paradigm within Lisp is based on this concept, and they're very much immutable, shared representation, all the rest of it. This is great. So what's that going to look like? Well, let's start off with an interface. What's that going to look like if I implement that in Java? So a persistent data structure. Let's try representing it using a different technique. What I'm going to do is I'm going to represent the state model very directly. I'm going to say I'm going to have a class that represents empty stacks. Now, you might say that's not very useful, Kevlin. I have a class just for empty stuff. Yeah. Well, what's its depth? It's always 0. Can you take its top? No, it's always illegal state exception. What about pop? Always illegal state exception. What happens when we push? Well, you return a new non-empty stack. Ooh, that's exciting. We're not actually changing anything. Now, I'll just factor out a trait method there for brevity, because that's the same in both cases. What about non-empty? Here we actually have to hold something, but again, if we look, what's the depth? It's 1 plus whatever the rest of the stack looks like, whatever the depth of that is. What's the top? It's the top item that we hold. What's the pop? Well, it's the tail. This is quite interesting, because if you look, there are no if statements. What we've done is we've actually represented, very much like the gang of 4 state or objects for states pattern, we've represented 2 different types for 2 different states, emptiness and non-emptiness. But everything is immutable. It also satisfies a very amusing idea. I don't know if you've ever come across this, the anti-if campaign. The anti-if campaign is like, we need to get rid of ifs because they are dangerous. There are no ifs in that code. The goal of the anti-if campaign is to raise awareness of the effective use of software design principles and practices by, first of all, removing bad, dangerous ifs. Okay, you have something to do on Monday, all right? So find those if statements. There are no if statements in the code I've shown you. It's all done through polymorphism, the magic and wonder of polymorphism. Okay, let's go back to that. So here's the original mutable stack. Stack of string is a new stack, and then I'm going to push GeeCON, I'm going to push Prague. Okay, what's the change in usage? I'm going to start off with an empty stack, and then I'm going to push, I'm going to chain it. So what we do is that now, instead of having modifier methods, we always return the resulting data structure, but it's not expensive. We're not returning a new internal array list every single time or something. We are returning a view of something much larger. However, there are some limitations that unfortunately we hit in current versions of Java. The assumptions are whatever type you're dealing with, it must either be immutable, so string works very well, or you've got to guarantee in some other way that it remains immutable or unchanged. Just like the keys in a map. Okay, you're not supposed to change the keys in a map once they're in the map and being used as keys. Otherwise, you get surprises. In other words, you break the encapsulation. So the illusion of this data structure, and remember, all software is illusions, all code is illusion, is that everything is shared, everything can be shared because it never changes. But once you get immutability, it actually has a fundamental shift. So in languages that support that, that's definitely my favorite article title from last year. Immutability changes everything. Why? Why? Well, it allows us to reason about our code. It allows us to share representations. But also, it allows us to handle concurrency much more easily. So, this is taken from a TV program that was the BBC aired in about 1984, if I remember correctly. The program was called Threads, and it explored what would happen in the event that Sheffield in Yorkshire, in fact, if there was a global nuclear war, but focused on Sheffield specifically. And it was utterly grim. This is the height of the Cold War. It was utterly depressing. I remember going into school the next day, and there was silence. In our group, it's just like, wow. The year before, there'd been an American film called The Day After that showed what would happen to America in the event of a nuclear war. Tell you what, they have it. It looked great. Threads told you about death, but they were having a soap opera in America. This was much more convincing. Anyway, this is relevant now. Apparently, we've gone back to have a slightly warmer Cold War than we used to. So I feel I'm going to bring nuclear depression on those of you that are too young to have really experienced the joy of being on one side or the other of the curtain during the Cold War. So welcome to the 21st century. I hope that works out for you. So threads. This is how I also want you to think about what happens to threads in your code. When you introduce threads, it's a different kind of atomic devastation, okay? It's kind of like there are problems. Now, the problem is that people say, oh, well, that's really bad, you know? We have a solution. We have locks. We have locks. It's like, no. If you want to reason about the stuff clearly, here is a very simple quadrant diagram. If you want to know how quadrant diagrams work, there's normally one thing that's really, really bad or one thing that's really, really good. Let me just show you the really, really bad one. Red is the color of danger, okay? It's nature's way of saying, don't do this, okay? That's that bit. That's the synchronization quadrant. You can have data. The data can be shared between threads or not shared between threads. It can be mutable, it can be immutable. It turns out that 3/4 of the quadrant diagram, it's really easy to program in. Because either you don't share things, so you can change it if you want, but nobody else gets to see it. It's true encapsulation. In other words, you cannot tell if somebody else is changing state. This is why we have this rather interesting outcome, for example, in Unix-based systems. There's a very strong idea of composing things on the command line. You have a command line which allows you to pipe and filter things together, which is actually a functional paradigm, a data flow paradigm, yet the internals of the process can actually be quite imperative and involve state changes, but you can't see the inside. So there's this whole point of like you isolate, you genuinely encapsulate the degree to which state can be modified. You can't see it. Alternatively, you say you can't change it, therefore we can share it freely. 3/4 of the diagram is really easy to program in, but guess where we end up coding? It's like, oh, you know what, that's all too easy. We're going to go for the top right-hand quadrant. And you ask people, so why is it that you are doing, why have you got all these locks? And people say, oh, safety. Yeah, but why did you do threading? Speed. Okay, things to remember. All computers wait at the same speed. A lock, the purpose of a lock is to prevent concurrency. Yeah? It's just like, yeah, it's a really fast car that you've got there, yeah. And you know what? I can put my foot on the accelerator and the brake at the same time. It's like, no. The point here is if you care about scaling, composability, and all the rest of it, you want to get away from this. So, there's a point here which I think is really interesting, and there's a relationship between paradigms. I'm just going to pick on object orientation and functional programming rather than other imperative and declarative paradigms. OO makes code understandable by encapsulating moving parts. Functional programming makes code understandable by minimizing moving parts. It's that minimization. In both cases, we're getting something, the ability to reason about and potentially scale the code. But they have slightly different philosophies. But they're not so very different. Let's go back and revisit our friend, the stack. Let's go and have a different stack. This time we're going to have a proper conversation. What we're going to do is we're going to treat a stack as a first-class process. And our conversation is going to be based on the idea of we can push and we can pop, but also it talks back to us. Instead of, we're actually going to go for a message-based paradigm. Instead of having a function return, we're going to have a message-based paradigm. And so when we talk to the stack, it can send us back a message. It can say, hey, look, guess what? You tried to pop something, and here is the popped item. I deliver you the result. Or you tried to pop something, but I'm afraid I was empty. I have nothing for you. Okay, so we've now got a two-way conversation. This is great. So there's the work that you want to give somebody else. Actually, we can do this more nicely here. So we have this very simple idea of I'm going to show you what messages are sent out. So pop is an inbound event, and empty is an outbound signal, or an outbound message. Okay, so you've got a nice kind of simple approach. Right, what language am I going to use? Well, there is an Erlang for the JVM, but I'm going to use Erlang because it does a really good job of this. But it also gets us talking stacks of multiple types, and it gets us thinking about things from a different angle. First of all, we're going to have an empty thing, because we broke it into empty and non-empty. Right, there is a primitive concept. You can receive, and you can receive an action. In fact, it turns out that Erlang has very few control structures. You can receive something, or you can have an if decision, and that's pretty much it. Receive, well, you can receive a push request. So I've got here, push is a symbol, that's our push request, top is a variable, that's the value we're going to push. So what do? Well, we call non-empty with top. Okay. What else can we receive? Well, pop, and we receive a return address. It's very polite. You get to say, I would like to pop something, please send the result back to me, or you can send it to somebody else if you want. So that's the return address. Fine. And because in the empty state we have nothing to return, we just return the symbol empty. We say, yep, we're empty. And then we loop back. This is tail recursion. We return that. Now, some people get very frightened of tail recursion because it's just going to disappear off to infinity. Fortunately, most sensible systems have tail recursion, tail call optimization, but this is the one true way of doing iteration in Erlang. And if you're wondering, this is what is called, this is a very true and pure and original form of the actor model. That's what we've got. We've got a function that can receive interactions. You cannot see the function from the outside. It can receive events via an identifier, but that is it. Right, we need to look at non-empty. Right, we take a value, we receive, and we push top. Well, we become more non-empty. So now it turns out what we're actually doing is we're using the call stack to hold our state. So a function has state in its call stack. When we return from being non-empty, we continue being non-empty. If somebody wants us to pop, we return the value that we currently store as value, and then we return from that function, dropping down the stack. So actually, we're accumulating our state in the call stack and receiving requests and pushing and popping accordingly. So it turns out there's something very fundamental about stacks here, and it's a really nice example to illustrate a very pure actor model. Actor models have become popular, but they're always somewhat less pure in implementation. So the Scala model is much less pure than this. This is surprisingly straightforward. To see, there's this wonderful observation, XKCD. Of course, it's wonderful observations. It's always wonderful observations. Why do you like functional programming so much? What does it actually get you? Tail recursion is its own reward. Again, if you don't get why that's funny, there is time to look at this later. But this I love. Functional programming combines the flexibility and power of abstract mathematics with the intuitive clarity of abstract mathematics. It's like a comment I once read of C. C combines all the power of assembler with all the readability of assembler. So we've got an idea there. Now, we can see ourselves interacting with it. We're going to create a process stack. We're going to pop. We're going to self is ourselves. So we pop something. It tells us we get a return empty. So there's nothing there. We push 42. No response. That's fine. We pop self. We get back a message, a tuple that says, hey, guess what? Popped 42. Okay, we can push 20, push 17, and then we pop. We get 17 back in reverse order, stack order, and pop. So we can actually interact with this running function in a separate thread. And notice nobody's seeing threads. I'm using the term thread for familiarity. But what we've got is really a communicating sequential process, but it gets born of a function. Now, what is fascinating about this is people say, this is pure functional programming. Yes, it is, and it's pure object-oriented programming as well. This is one of those interesting cases where paradigms end up unifying through similarity at a different level. Paradigms are not normalized. They are not, there's no kind of like, you are now leaving the object sector and entering the functional sector. They overlap, they're messy, they're sloppy. Not all functional programming languages have the same concepts. Not all object-oriented programming languages have the same concept. Alan Kay, originator of Smalltalk, object-oriented programming to me means only messaging, local retention and protection, and hiding of state process, and extreme late binding of all things. That is exactly what the actor model is. Oh, there's an interesting thing here, which I'm going to bring back to a quote that I've used a number of times, taken from William Cook's paper on understanding data abstraction revisited. He talks about abstract data types. He talks about object-oriented programming. And he makes a really interesting observation. He says Lambda calculus was the first object-oriented language. This is a really interesting thing, because we normally think of lambdas as being a very functional thing. But it's this idea that they can retain some kind of state. Now, he puts 1941. I did a bit of digging around. It turns out it's 1932. So, when people got really excited, it's just like, yay, Java, finally, it's got lambdas. It's just like, yeah, programming like you're in the first half of the 20th century. Yeah, the ultimate retro. That goes way way, way earlier than any of the other papers I mentioned. So, the home straight, I want to look at, what is that? Oh, great, I get to use Lambda symbols as well. So this is how we can define a stack in a way that pleases some people mathematically. But instead of doing this, I'm going to use JavaScript. I'm sorry. Okay, so you know, I could have used a programming language, but you know, time is short. So what I'm going to do here is I'm going to give you a different view. It's the kind of function as object or almost module type approach. It's interesting. Hiding within JavaScript is actually a very pure object model. It's just not the one that most people use. So what I've got is new stack. I'm going to say, right, a new stack. When I call new stack, it's a function, but it yields. What does it yield? A pure closure. I have an array called items. And then I return you. I don't return you a thing in the classic sense with state. What I do is I return you a set of operations. I return you a dictionary or an object that contains operations. There's an operation called depth and top and pop and push. And these capture the closure of the local variable items. There is no way anybody can get their hands on that private state. It is truly private. And so this is a sort of simple implementation, or we could use the push-pop approach. Both of those have exactly the same behavior, and that's quite important. Okay, so this is a very pure object model, very, very late bound. But you know, I've shown things like this before, but I think what was more interesting to me was recently I started thinking, well, hang on, what about inheritance? How do we do inheritance in this model? Well, it's a small change. What I'm going to do is I'm going to introduce the idea is that a function doesn't just associate. What it does is it takes some state and then it associates any extra state and any extra methods that you need and returns those. And it merges those. That's what the object.assign is doing. So here we have, you know, something, we're going to call it stackable, and this actually follows, if you've ever come across the mixin idea, this follows very closely the idea of mixins. You can kind of get close to that with Java 8 traits, but not quite. But you know, what we've got here is what you do is you take something and you say, right, my new stack, I'm going to take that function that I had before, and I'm going to say, I start with an empty object, open, close, curly, and it's stackable, and that now gives it stackability. And so now I can call new stack exactly as I did before, and this is great, but it gets more interesting, because I've inherited from not a lot. Now let's actually inherit from something more, do something more meaningful. Let's make our stack clearable. So what I'm now going to do is I'm going to add the ability for it to be clear. So you can say clear and it will empty it while there is depth, then call pop. So now you can call clear on it. So now what this looks like is new stack is clearable of stackable of empty object. So you take an empty object and you apply, you mix in stack behavior, then you mix into that clear behavior. So this looks like composition, and in fact we can create a composition. So it turns out inheritance can be understood as a composition. So it's an interesting kind of crossover between functional and object-oriented thinking. Now, JavaScript doesn't come with its own compose. You can do that as a reduction. It's a fold. I'll leave that one for homework. And you might be tempted, hey, wait a minute, I can do overriding as well. Yes, you can. It's great. You just sort of take something and we're going to rebind the push operation. Here, I've got the idea of having a non-duplicating top. If you push something that's already on the top, then it ignores it. Okay? So if the base top does not equal the new top, then we'll push it. We'll use the base version. Otherwise, we'll just ignore it. And people often use inheritance like this. Okay? So I'm going to suggest one thing. Don't do that. Why? Barbara Liskov, again, she's getting featured quite a bit today. Has anybody come across Liskov's substitution principle? LSP, yeah. The L in solid principles. It is widely misunderstood, but this is the paper, 1987, on data abstraction and hierarchy, where she talks about it. And she says a number of things, and obviously she has to phrase it formally. A type hierarchy is composed of subtypes and supertypes. The intuitive idea of a subtype is one whose objects provide all the behavior of objects of another type, the supertype, plus something extra, like stackable, clearable. What is wanted here is something like the following substitution property. If for each object O1 of type S there is an object O2, this is the bit where it gets boring, of type T such that for all programs P defined in terms of T, you can tell somebody wrote this out on a whiteboard using upside down A's and then translated it into English. It would have been much better mathematically. P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. Now, this is a few pages into what I think is a classic paper, and most people, their eyes slide off this paragraph. It's very often quoted, but it has some interesting implications. Let's actually look at what these implications are. So, this is a test. You can, it's an ad hoc testing framework that I sort of threw together to just check that my stack did actually do the right thing. So, I've got a simple, one of my tests, a non-empty stack becomes deeper by retaining a pushed item as its top. And then I've got this stack, I've called new stack. I push GeeCON, I push Prague again. The depth should be 3. The top item should be Prague, okay? If I have new stack being the composition of clearable and stackable, so it's stackable and it's clearable, and it inherits in that sense, then, the test passes. That's green. That's great. What happens when I also throw a new non-duplicate top? It fails. It turns out that many people have kind of misunderstood the implications of the Liskov substitution principle. In fact, and it's not an abstract idea, it's a very concrete idea. I can write a test to show you how Liskov is violated in this case. The problem is that we said that for the base, the super, that whenever you push something, the height goes up by 1, and the top item is whatever we left there. The height always goes up by 1. The problem is that here is a test that demonstrates that when you've inherited and overridden it, so sometimes it goes up by 1, but sometimes it doesn't, actually it fails. So this is an interesting thing, is that Liskov is actually a thing that you can test. You can write a unit test for, and things can pass and things can fail. It's not a fluffy abstract idea at all. It's very, very concrete. So this stack with non-duplicate tops does not satisfy the stack contract. As I said, the contract is much larger than just simply the idea of pre- and post conditions. It's something else about what we can expect, and that's simply one way of phrasing it. So, this is the relevant bit. For all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2. That's the relevant bit. So, in closing, given that I chose books, given that I've chosen a number of papers, given that people often refer to these papers, I want to kind of close down on the fact that we've looked at a number of things that are of interesting knowledge, but in some ways they're very fundamental and they are timeless. All of this stuff is old, but we often are in such a hurry to move to new solutions that we forget that there are ideas that could really save us a lot of work, or that there are ideas we've heard of but have greater depths. I think, for example, that the Liskov thing is interesting because that paper is freely available, as most things are on the internet. Angela Carter's quote, a book is simply the container of an idea like a bottle. What is inside the book is what matters. Sometimes you have to really go inside and actually have a look. What is this person actually trying to say? It turns out that many of the principles that we overlook are hidden, but known, are hidden inside some really interesting blog posts, interesting papers. But also many of the ones that we misunderstand, the truth is in there. So we need to think of, when we think of full stack, I've used stack as a gratuitous example to allow us to explore some very fundamental but often overlooked techniques. I've tried to show the connection between them. I've also tried to use this as a way of saying you need a bigger picture as well when you come to this stuff. It's not enough to know one thing well and one architecture and one tooling well. There is a bigger picture. As Grace Hopper observed, to me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. And I hope that, if nothing else, makes you want to go out for a beer or cut some code. Thank you very much.